Hello and welcome. Today we'll be talking about an interesting topic in the mathematical world known as the golden ratio. The definition of the golden ratio can get kind of confusing because the wording of it is a little bit hard to follow. The definition states that the ratio of the total of the parts to the largest of the parts is equal to the ratio of the largest of the parts to the smallest of the parts, and we denote this ratio by the Greek symbol phi. The easiest way to understand the definition of the golden ratio is by using a line segment. We have this line segment here. We'll call it A plus B, where the largest of the part is A and the smallest of the parts is B. Now the point in the line segment between A and B is phi. To find that point, we need to set up a ratio where A plus B over A is equal to A over B. The discovery of this ratio is attributed to the Greek philosopher and mathematician Pythagoras. While it's unclear if he himself discovered one of his students, it is still credited to his name as was the tradition of the time. The reason the Greeks were so interested in this ratio is for the fact that it shows up many places in nature, and is also seen by artists as being one of the most aesthetically pleasing ratios. It is now possible for us to calculate the exact value of the golden ratio. To do so, we'll look back at that line segment we had in the beginning. So we'll let the whole line segment A plus B equal the number 1. We'll let the largest of the parts A equal x and the smallest of the parts B equal x minus 1. Setting this into the ratio, we come up with 1 over x equals x over 1 minus x. Through cross multiplication, we get 1 times 1 minus x equaling x squared. Then by setting it to 0, we are left with a quadratic x squared plus x minus 1. Now, we have this quadratic. What we need to do is we need to factor it. The only way to factor is by using the quadratic formula. So we'll have negative 1 plus or minus the square root of 1 squared minus 4 times 1 times the negative 1 all over 2 times 1. This will leave us with a minus 1 plus or minus the square root of 5 over 2. And of course, we're going to use only the positive value here since we're dealing with lines and lines can't be negative. Our original ratio. So we'll plug it back into the 1 over x. So we'll have 1 over negative 1 plus the square root of 5 over 2. And when we evaluate this out, we get approximately 1.6180, which is the golden ratio. Now, the golden ratio, being such a unique number, has several interesting properties. One of which goes back to our quadratic formula. Remember when we factored and we had that negative answer that we threw out? Well, now if we substitute that into the same 1 over x equation, we wind up with 0.6180, which is in fact the golden ratio to its negative first power. Another interesting property of the golden ratio is that phi to any power is equal to the sum of the two immediate preceding powers. For instance, phi to the first power is 1.6180, which is phi, and phi to the second power is 2.6180. When you add these two numbers together, you get 4.2358, which is phi to the third power. The golden ratio won't only pop up when we're talking about a line segment. The golden ratio can be found in any geometric figure. 3 of the most known and seen throughout the world are known as the golden triangle, the golden rectangle, and the golden spiral. Here we have a picture of the Great Pyramid of Giza. As you can see, a triangle is inside the Great Pyramid of Giza, from along one of the walls to the outer edge, to the base, to the middle, up to the middle of the top. And with these numbers constructed, we come up with approximately the ratio of 1.61950, which is surprisingly close to the golden ratio. It is believed that this pyramid was intended to be built as a golden pyramid using many golden triangles, and getting that close with such primitive calculating tools is quite an impressive feat. We see a picture of the Parthenon. Now, it's said that every geometric figure used to design the Parthenon was built to be in the golden ratio. They did this in order for the building to be more aesthetically pleasing, as this was once again the popular belief of the time. Here we have a cross-section picture of a very common shell seen in the oceans throughout the world. Now, if you start at the center of the spiral that is seen through this cross-section and look at the logarithmic growth along the shell, it is in exactly the same ratio as the golden ratio. So this is what is known as a golden spiral, and this particular one appears in nature. This will now conclude our introduction to the golden ratio. Thank you for watching. Have a great day.